Well, hello everybody and welcome to our webinar. My name is Marina Silva and I'm representing Integrated Global Services. I'm joining you here from England, and just so we know that you can hear us and you can see us, could you please type in the chat where are you joining us from today? And I will start this. While we're waiting for your confirmations, great. In this Fuel Masterclass webinar, we will talk about the latest insights into fuel selection for your power plant. Now let's say hello to our speakers. We have Dr. Gerry Riley here from RJM.
Hi everyone.
And Gerry will demonstrate why it is necessary to have a thorough understanding of the risks that a change in fuel may introduce, and show how modifications to material handling and primary combustion systems can ensure optimal performance with emissions compliance following a fuel switch. Then we have Colin Bateman from IGS.
Good morning, everyone, or good afternoon.
And Colin will explain how to resolve boiler fireside erosion and corrosion issues following a change in fuel diet. Then we have Ulf from ECOMB.
Hello.
Hi, Ulf. And Ulf will show how to mitigate new combustion issues introduced with the new fuel, cut fuel costs, and reduce pollutants such as NOx, CO2, and VOCs. And then later on today, the final presentation will be delivered by Vince from PowerPlus Cleaning Systems, and he will explain how the buildup of slugging on convection surfaces in boilers and heat exchangers can be virtually eliminated. Right, some housekeeping before we start. The webinar will take about 2 hours in total, and we'll have presentations, interactive question and answer sessions, and polls. You can type your questions in the questions tab on your right. We will have 5 minutes of Q&A session after each presentation, and then a longer roundtable at the end of all 4 presentations. So please stay until the end to get all your questions answered. We're of course broadcasting live. If you experience technical difficulties, refresh your browser. If that doesn't work, switch to a Google Chrome browser, or you can dial into this webinar to get the audio. I'll post the dial-in numbers in the chat now. And you will need a dial-in code as well. Also in the chat. Perfect, so I will hand this over to Gerry.
Hello everybody. Can you all hear me? Oh, Marina, can you hear me?
Yes, I can.
Yeah.
Fantastic. Let's go. Okay. I'm going to sort of act as a guide to talk you through the topic today. My background is that I've been working in the utility and industrial boiler sector for nearly 35 years. And I've been looking at the impact of fuels on the operation of the plants for this period. I first got involved in trying to come up with some sort of procedural approach to dealing with risk when I was working with a large utility in the UK. And it was seen that the cost of fuel was so phenomenal that the risk of getting things wrong was a potential problem for the company, and they wanted some sort of risk process put in place. So what we're going to talk about today, sort of, we're going to look at this from a very high level perspective rather than go into details, and it's all about identifying potential risks and then determining whether that's something that you want to mitigate or whether you need to sort of avoid. And this can be applied to a simple fuel change, say if you're wanting to look at a different type of wood pellets or a different type of coal, through to a significant change in your fuel diet, whether you want to switch, say, to 50% co-firing with a new fuel or even to a full conversion. Okay, so we're going to start the presentation now. I hope you find it interesting. There'll be a few questions popping up in the chat that we hope you will get involved with, and we look forward to hearing some interesting questions at the end. So let's begin. I work for RJM International. We're a company that specializes in resolving complex combustion and emission challenges across the utility and industrial boiler sector. We can resolve problems related to all fuels and all boiler types, and we've got a track record of delivering such solutions. Today we're going to be talking about fuel switching, and fuel switching could be anything from changing the basket of fuels that you burn through to something more complicated like a complete conversion from one fuel to another. There are many reasons why you would want to do this. Often the biggest one is cost. A fuel that you're burning has become more expensive than you want it to be. Maybe the economics of the plant don't allow you to continue with that operation, so you have to find some way of diversifying. It may well be that actually the fuel that you've burnt for many years is no longer available. So it could be something like that where you're being pushed by an economic reason. But equally, it could be due to legislation where the governing body has decreed that you have to reduce sulfur emissions or other emissions, and this means that the fuel that you've been used to burning is no longer as attractive. Or, as we've faced in the UK, it could simply be a political decision. The government have decided that coal is out, and therefore all those plants have to either close or find another fuel. Now, at the center of all of this fuel switching is the risk. And as I said, I've been in this industry for too many years now, and I have seen so many examples of where wrong decisions have been made very early on because of a lack of understanding of the fuel. So the key to a lot of these projects is understanding the fuel. If you don't understand the fuel, you can make mistakes. I've seen it many times in the past. A poor decision will persist for the lifetime of the project. And if that happens to be in the design stage, then it will last for many, many years. The most important thing is to try to avoid unexpected consequences. Most of them are foreseeable. We have to identify the risks, and they generally fall into three categories. There's a regulatory risk, commercial, and technical. We'll focus today mainly on the technical side of things, but these other two aspects do need to be considered. Clearly, if you want to switch fuels at your plant, you need to know whether you're able to. Does the permit of the plant allow you to switch fuels? This generally is more of a problem when you're dealing with waste. You also need to think about the commercial aspects. Is the fuel available in the volume you need? Is it at the price you need? Is price stable? I mean, what you often see is that with many fuels, the price varies through the year. And that could be a factor that you may be evaluating it now when it looks commercially attractive, but in a year's time, is that going to be a problem? Because you may make some decisions which means you can't switch back. So it's important to understand those. But today, mainly, we will talk about the technical risks. And whenever I am faced with this, there are four questions that I ask. Firstly, can we do it safely? Because if we can't, then it's a stop. Can we meet our environmental limits? Again, if that's no, then you can't proceed. We need to think about the plant operation. There are some fuels which can result in unplanned shutdowns. So that clearly links into the operating mode of the plant. If you are dependent on high generation, high availability, then this may be an issue. If you're not, then perhaps you can manage this. And then there's the due regard to the plant's integrity. Very rarely do you do a fuel switch from a particular fuel to a better fuel. It's generally you go down in quality. And very often when you go down in quality, there are many issues which do relate to plant integrity that you need to be thought about. And we have a presentation later where we will discuss this in a little bit more detail. And finally, when you put all these things together, is how much will it cost you to burn this new fuel compared to a reference? The cheapest fuel doesn't necessarily make the cheapest steam or electricity, and that needs to be borne in mind. To avoid missing risks, it's important to have some sort of process so that a new fuel can be assessed. Now, the level of assessment will be very much determined by the percentage replacement. For example, if you were just adding a new fuel to an existing basket of fuel for the station, i.e. you were replacing, trying to find a new wood pellet for an existing sort of plant that burns wood pellets, it would be 1 degree of assessment. Whereas if you were suddenly saying, well, actually, we'd like to bring in a totally new fuel to that station, then a different level of assessment's required. As well as if you were doing, say, 5% coal-firing replacement, you would need 1 level of assessment. But if it was 50 or 100%, then the effort required and the cost would be significantly more. And what you would expect as you increase the percentage replacement, your return will obviously be bigger, but the risk will be bigger. And the chances are that you will need to spend some money to enable you to do the conversion. That said, the basic considerations are the same. Now, if we think about the risks, let's start with material handling. So this is just a schematic of an imaginary material handling setup. So the sort of things that you would need to consider would be the storage of the fuel. Are there any risks with it self-heating, causing fires? Are there problems with, say, fugitive dust? Is the material suitable for preparation as any other fuel would have been? Is there a risk about tramp or variability? And also, is there a problem then with health and safety aspects that the previous fuel has not had? All of these things need to be thought about, and clearly when we're looking at this, you need to think about the characteristics of the fuel. Does it flow through the bunkers in a similar manner to a previous fuel? Is it sticky? And so on and so forth. So there's a lot to consider, but if there's a structure there that covers these, you will not miss things. And similarly, if you think about combustion, you've got to think about things like if you have a grate or a bed, is there an issue with potential sintering or overheating of the grate? Is there a problem with slagging or fouling, or boiler corrosion? What about the heat release? Does that change when you move to this different fuel? Can this be burnt in a stable way? And can you control the combustion? So there's quite a lot of things that you need to think about within the boiler. And then obviously you've got to think about the air pollution control equipment. And here we're looking at NOx, SOx, particulates. If you're dealing with waste material, then you might need to think about the polyaromatic hydrocarbons or PCBs, dioxins. And then finally, one of the elephants often in the room is the ash. What do you do with the ash? Is there a problem with the ash? Because certainly in Europe now, ash disposal is very, very expensive. So these are the sort of structures these are the sort of things you have to think about. Now, I'm going to just talk you through a very simple case study to give you an idea of how you can use this type of approach. So we got involved with looking at an end-of-life coal plant that was looking for a cost-effective option for continued generation. They'd looked at biomass and it required subsidies. So they came across the idea of trying to use waste materials to produce the electricity. Now RJM got involved in the initial scoping of the project and identified that in theory it was possible. Obviously, the beauty about using waste is we have a world problem with global problem with waste, and this is a potential solution to deal with the end of life material that is likely to go in the ground if we don't deal with it. and it was thought that this could become a pilot project for a rollout around the world. Now, well, this is a bit of a sort of challenging slide. So when we started the initial assessment, we identified a series of risks, and what you have here is a representation of some of these risks. And red highlights potential showstopper. So these are things that we have to get some form of mitigation in place for. The yellow risk is something that we think we have got our hands around and we can manage, and obviously a green risk is something that we're happy with. Now, what I'm going to do is I'm going to use this slide to jump in and out of different areas and just talk through a little bit of the background to them. They won't necessarily relate to the waste sort of case study, but hopefully will give you an idea of the sort of things that needs to be done when you start looking at risks and mitigation. So the first area that we're going to look at is just some material handling type issues that you may come across. I've got a few pictures here of some of the issues that you may encounter when you switch fuels. So on the left, you've got I think it's a soot blower underneath all of that mess. And what's happened is it's a biofuel. It's obviously been present there for some time, and you've now got fungal growth. So clearly there's a health risk associated with that. The middle picture at the back is the delivery of a fairly dry biofuel, and you can see the dust that is blowing around. Well, obviously dust is a health risk. Inhalation of certainly wood dust is potential carcinogenic, but it is also a concern in terms of safety. Explosions are common with this type of material. Underneath you have a sort of blow up figure of the fibers in a particular fuel. Now this is one of the big issues that you are faced with when you switch fuel. You could potentially have a granular fuel as your base fuel, and then suddenly you're asking equipment that is not designed to manage this fibrous fuel to deal with it. And the risks are then obviously that there are blockages and holdups within the silos, etc., etc. So these are the things you must think about. And then over on the right here is what happens when it goes wrong. So the dust there has settled and has caught fire, and this is a boiler house on fire. So concerning material handling, there are these various things that you really must think about when you look at things. Now, this is an example of a problem we came across at a site where when we got to site, they were experiencing inconsistent fuel flow and limited throughput. And what we found when we did the analysis was that the flow within these metering bins was not mass flow. They were actually getting a rat hole at the back of the bunker, which meant that the screw wasn't being fed and filled properly. And also with the design of the screw, because it was a fixed pitch, it was blocking, it was filling at the far end here on the left, and then it didn't allow material to drop down into the chamber. So it was a pretty poor design. We then identified a few things that were problematic. This system didn't provide a air seal, so we put in a rotary valve. We found that there was the actual metering bin was poorly designed, so we rebuilt that with the avoidance of any sort of ledges or what have you that would cause or initiate buildups, and then we redesigned the screw. Putting all of these things together, we managed to increase the throughput of the screw by about 40%, which gave them the throughput they needed, and it was also associated with a much better stability of the feed. Now we're going to just look at the issues related to combustion with changing fuels. Now, I was always led to believe that great boilers were very forgiving, And I think it's only in the recent sort of last 18 months I realized how flawed that view was. I mean, as we know, grates are very simple, but they have to be tuned to a particular fuel. And by that, you have to have a certain length of the grate for the combustion. You need to design the airflows and such likes, and also the material and the way the fuel is fed to it. So they are actually tuned to the fuel. So if you suddenly introduce a new fuel, these are the sort of things that you have to consider. So very often you end up potentially with a drier fuel. So many of the original grates were designed for coal, and they're now being asked to burn biofuels, wood pellets, and obviously these are much drier. And then you have this concern that you have to deal with the much hotter fuel on the grate. And this image here, which you may be able to see, is you can see a damaged, a warped grate bar because it's overheated. So these things have to be considered. You may end up with a wetter fuel which takes longer to burn or longer to ignite, and therefore you have to adjust the flow. If you're dealing with a lower ash coal, then you've got a concern about covering the grate. So there's all sorts of things that have to be considered, even with a system which you would think is very forgiving. Now I'm just going to take a little bit of a deep dive into the combustion of the waste material. Now this is an example of the stages that you would expect to go through with a complex project. So in the initial stage, stage one, this is very much the scoping, looking at the risks, identifying the risks, and determining whether they appear to be something that you can live with. If it's believed that these risks can be mitigated, you would then be able to go through a gate control and into the stage two, where you would look at some more detailed analysis. Now this would obviously involve looking at maybe some specialist testing, combustion testing, things like this, to give you more confidence that the mitigation you've identified is acceptable. And then if that all comes together, you can go through a gate review, which will then allow you to put you into the, I guess, the detailed design stage of the project, which would allow you to identify plant modifications, engage with the market for quotes on equipment. You can define the project, and you can come up with a proper budget. This will all allow you to put together a basis of design for the upgrade, and hopefully allow you to get to financial closure. Now, when we were looking at the waste, one of the problems that we were faced with was that waste combustion and CFD isn't that well developed. And what we have here is we have a diagram which is looking at the different stages of combustion for coal, wood, and plastics. And you can see that the plastics are significantly different to coal. You go through a sort of melting phase and evaporation, and that's something that hadn't been modeled or wasn't in any of the CFD models that we were standard. So this was an area that we actually had to look at developing. And here is the degree of work that was involved. So we've got three elements to this. So we've got the fuel characterization work, which is needed to define the fuel so that we can then implement that into the model. And we're looking at things like the composition, the kinetics, the shape, etc. We then have the model itself. So as I said, the model didn't have the right components for plastic combustion. So what we have here is this is a user-defined function, which is a specialist function that you can add to a fluent model. And we built this UDF to allow us to model plastics, and then we can look at the sort of the meshing and the modeling of the work. and we can look at the heat balance. If we then tie all of this together, we need to validate it. So you would then need to do some form of validation, which probably would involve a combustion sort of facility. When we did that, we put all this together, and you can see here there's a combustion facility here, and there's one of our engineers sort of working with a probe to collect data. This allowed us to develop predict the model. This is our prediction of the flows within this furnace, and you can see from the images we have of the flame, and we use the data that we've collected, the in-flame measurements, the temperature measurements, to compare against the model and hence validate it. And when you put all that together, you're then in a position to actually do a model of a boiler. Now, this particular example isn't the waste boiler. This is a model of a boiler in Kosovo that we're currently working on, and what you can see here is a combustion prediction of NOx, and the over on the right there you've got a degree of NOx emissions. And that just gives you an idea of the sort of complexity that you need to follow with some projects. So finally, when we've been through this detailed assessment process, we've managed to move a lot of the red risks down into a medium risk. The project had still quite a long way to go before it got to fruition, but I think hopefully we've demonstrated that there is this process that one would go through to identify the risks, then look at mitigation. Now, there are some of these areas that we've not discussed, and we will now cover them in some of the additional presentations coming up.
Thank you, Gerry. I would like to welcome you back on stage now, and we'll run a quick Q&A session. So if you have questions for Gerry, please type them in the questions bar.
Yeah, we're sorry for the technical glitches as well. Yeah, I mean that's the life of doing things remotely and dependent on the technology. But if you have any questions, please ask them.
And we have some already, Gerry. So the first question is from Shaheen. How should a boiler be preserved when it's out of service for a long time?
Oh God, yeah, that's a great question. I think with things like that, it's all a matter of draining out the fluids, making sure everything is protected against corrosion, etc. So it's a long project, but I'm not sure that's really the question for today. That's another topic.
So is it something you will be able to get back to Shaheen after?
Absolutely.
Mm-hmm. Excellent. Question from Majid. Are you going to discuss the natural gas fuel, or maybe a conversion to natural gas?
Not specifically, but the process is the same. We've actually done quite a lot of solid fuel to gas conversions actually, and that is one of the things that our company is quite familiar with. But again, I mean, if there's a question there, we can deal with that later.
Thank you, Gerry. Question from Suresh. How good is the model prediction on a pilot plant versus an actual unit?
It's all depends on the quality of the inputs. This is the sort of the process that RJM goes through. We collect a lot of background data, carry out baseline tests, and when we do that, the confidence is the predictions are very, very good, and it's not unusual for us to predict an upgrade performance, and then when we turn up on the boiler, we can actually just go to those settings and we end up with the results, a complete sort of like-for-like sort of performance from the boiler. So yeah, it's they're very good if they're used properly. There is a saying though, and I'm told I can't swear, but rubbish in, rubbish out is a common feature with modelling. But if you put in the right information to start with, then yeah, you've got no problems.
Thank you, Gerry. Question from Muhammad. What modeling softwares can be used to see fuel change in combustion process inside the furnace?
I mean, we use computational fluid dynamics is the basic one. I mean, I think that's the one that's used by most people. So yeah, computational fluid dynamics.
Question from Andreas. Could you kindly explain once again what kind of risks can be eliminated to reduce by making CFD model? How effective is this?
I guess it depends what the risk is to start with. I mean, the whole idea is you identify the risk areas, and then it may well be that what you identify, say there is a heat imbalance in the boiler, and then you would have to modify the steam cycle to compensate for that. So it really depends what that is. I mean, what we find is that with using the CFD, you can actually tune the boiler to modify the heat release profiles. So I hope that's satisfactory.
Thank you, Gerry. Question from Aravinda Rajan. A follow-up question. What about flue gas emission standard?
What about flue gas emission standards? I mean, we operate to the, we will design the any fuel switch or whatever to the local standards. I mean, in the UK or in Europe, we're down to the equivalent of IED standards. So all of that can be modelled and dealt with. And this is one of the things that you really need to look at when you're starting out any fuel switch is what are the regulations. So one of the things that catches a lot of people out is if their plant is used to burn a fuel and then you want to switch to a waste, the regulations change. And that's where you can be caught out. So you do need to understand what emission standards you have to meet. But yeah, that's a relatively straightforward thing.
Question from Juliet. Is this related to coal blending? It's probably a follow-up to one of your previous answers.
No, this is related to anything. I mean, the whole of this process can be used on any fuel. It's just a protocol. If I said it was, it's like a HAZOP sort of. I don't know whether people are familiar with HAZOP. It's a hazardous operation, and you break the plant down into different nodes, and then you look at each node and you look at, well, what could go wrong. It's a similar sort of thing, that whatever the fuel switch is, you focus on each of the areas and you look at the characteristics of the new fuel compared to the old fuel, compared to the design, and you can then identify, do I have a risk in this area or don't I have a risk? And then where there is a risk, you've got to then determine whether it's at a level where it's a problem and needs mitigation, or it's something that you can live with.
Great answer. Thank you, Gerry. We'll take a few more questions and then we'll have to save others for the end of the event. Question from Muhammad. If the design on higher moisture fuel or coal, what effects in the process will be in getting lower moisture?
Sorry, can you repeat the question?
So if the design is for higher moisture fuel, what effects in the process will be if your fuel has lower moisture?
Oh, yes. I mean, again, there are so many things there, Mahab, and it's a really good question. The obvious thing to start with is that if you're using a drier fuel, it's actually probably a better quality fuel in the sense that it's a higher CV. But then that causes the issues, as we mentioned, with the likes of if you're using a grate system, that you have to make sure that the grate doesn't overheat. You also then have to think about the flue gas volume. You have to think of the heat release. So often, if you've got a high moisture fuel, you have a bigger boiler to compensate for the increased volume and the reduced radiation levels. But if you've got a very hot flame or a hot combustion zone, then overheating can be a problem. But with all of these things, there are mitigations. So the obvious mitigation when you end up with a a sort of a drier fuel is maybe you use flue gas recirculation to increase the gas volume and keep the temperatures down. So to everything, there's normally an answer. The question is, can you afford to pay for the answer?
That's a very good question. A question from Mark. How much do you take into account the contractual limits of the fuel, as these can be very wide?
Yeah, I mean, I didn't touch on that. That is a webinar in its own. You have to do that. You have to be conscious that the fuel, you can't just assume that you have one point. You have to consider the range. And you're right, if the contractual range puts you in a difficult position, then yes, that has to be factored into the evaluation. That's a really, really good question.
Thank you, Gerry. We'll take one more and then we'll answer the rest of the questions at the end. From Ahmed, what performance tests would you recommend if a plant considers moving from design call to a lower grade, a possible blended variant for reducing costs?
I think it depends on the type of plant, and it depends on how you're going to do your blending. One of the things, if you are dealing, say, with like a pulverized boiler where you have to grind the material and blow it in, then you need to think about how the blend is going to be introduced. Do you mix it with the original fuel, or do you deal with it separately? So those elements have to be considered. So you might need to do some tests on the mills. You would then want to do some sort of boiler performance tests. So you'd look at heat release, you'd look at steam flows and things like this. So you would do a whole set of tests. With a lot of these things, it would be your normal sort of guarantee or performance test that you would do at takeover. You would do a reduced version of that to evaluate the fuel, and you have to be careful. Going back to the question that was raised before, you may do your tests on a particular batch of fuel, and then the fuel may change. So you need to be mindful that what you're doing is just a snapshot.
Thank you, Gerry. And now I believe it's time to introduce our next speaker. And would you like to do the honors?
Yes. So when we were talking about, I'll just drop off stage now. People can still hear me, can't they?
If you come off stage, they won't be able to hear you.
Okay, right. So as we said, often we move from a higher quality fuel to a lower quality fuel. And the sort of issues that you find are that with the lower quality fuel, they may have a lot of chlorine in them, and then they become a risk in terms of corrosion. Now, it's very difficult to remove chlorine from a fuel. So then the next question is, how can you do mitigation? Equally, you may end up having to move to a higher ash fuel, and where there is ash, then there's the potential for erosion. So when we were looking at the waste project, we identified that the corrosion was a very, very big problem. We went to the market to understand what companies could help us, and we met our colleagues here at IGS who have some fantastic products. And Colin Bateman now is going to actually just describe some of these products in relation to the topic of today. So over to you, Colin.
Thank you, Gerry. And just before we pass it over to Colin, you are getting quite a lot of questions on your presentation. Even though we will go through them at the end during the roundtable, you're also able to answer them live in the questions tab. So we may do that as well. And now we would like to welcome Colin on stage, and we'll load his presentation up.
Good morning or good afternoon. Thank you very much for attending this event. Thank you to my colleagues for helping to set it up. This presentation is going to focus on how we can manage the effects of changing a fuel composition in a boiler in terms of protecting the boiler integrity from that change. In other words, protecting your water walls, particularly in the combustion zone, from the change in the environment that's caused by the change in the fuel composition. That's typically a change in terms of the chemicals that you see in that environment. For example, the addition of chlorine or addition of more sulfur. Sometimes a change in the temperature if we're burning a fuel that has a higher calorific value. And it means we need to look at what the current surface metallurgy is in that boiler and how we can protect that surface from the effects of metal wastage. One way we can do that is by upgrading that surface alloy, by installing a higher nobility material that is going to provide that corrosion resistance that we need, as well as the erosion resistance, in order to maintain the integrity of our boiler and of our water walls. And this presentation is going to look at a couple of technologies in order to resolve or to carry out that service. So here's a photograph of one technology being utilized to apply a surface alloy upgrade. This is a high velocity thermal spray process being applied inside a boiler. And the techniques we're going to talk about today are field applied techniques that can be carried out in situ in the boiler during scheduled outages. There are options in terms of panel replacement in order to upgrade surface metallurgy. Sometimes that cannot be the most attractive option in terms of time to carry out the repairs and that knock-on effect from a point of view of opportunity cost in the operation of the unit. So the applications and the technologies we're going to look at today are based upon in situ applications in the boiler during shutdowns and turnarounds. The first thing we need to do is to understand exactly how that boiler operates and what this change in fuel composition is going to do to the operation of the unit. Like Gerry spoke about before during the RJM presentation, there's many aspects that we need to look at when we're thinking about changing the fuel composition. The burners we have, the quality of the burn, the type of environment in the combustion zone, how that environment is going to be affected. So we need to look at the boiler type, and obviously we need to look at the fuel composition and how the change in that fuel composition is going to affect that combustion zone. Temperatures can be critical. We'll look at that in a little bit more detail later on when we're thinking about different types of surface protection technologies, obviously the pressure in the boiler and where the boiler is located. So once we've assessed all of these things, we can then start to look at what type of solution we need in order to overcome these challenges. So a key aspect of that analysis is going to be the corrosion mechanisms that are taking place inside the boiler with the new fuel composition. And IGS is a company who have 40 years of experience of working in boilers, specifically looking at corrosion and erosion metal wastage mechanisms and understanding how these mechanisms work. We have a sophisticated laboratory with advanced research and development capabilities for metallurgical development of different alloys, testing of those alloys, and also complete failure analysis. So including metallographic analysis using scanning electron microscopes to look at exactly what mechanisms have been going on and how these failures or how the metal wastage process is being carried out. And based upon that experience, we have a good, a solid, and a deep understanding of the different mechanisms that can take place and how they can be addressed in the boiler. As we've discussed before, changing the fuel composition is going to change that environment. The fuel diversification is going to cause a change to that corrosive mechanism that's taking place. The most common aspect of that's considered when we think about burning a biomass or a waste product, a recycled material or a reclaimed material, is an increase in chlorine. And that can come from many different sources, obviously from waste materials, from paints, from materials that have been recycled, etc. That chlorine gets into the combustion environment and can create a very different and much more aggressive corrosive attack to the water walls, ultimately leading to localized pitting and then failure of the water walls, leading to unplanned shutdowns of the unit. So upgrading the tube surface metallurgy to an alloy which is resistant to those environments facilitates that change and that diversification in the burning of different fuels, and of also switching, during the operation of the boiler in between outages without having to carry out another change, switching between different opportunity fuels, which can be dependent upon availability, dependent upon cost in the marketplace, etc. When we think about an alloy upgrade in a waste to energy or a biomass boiler, we typically think about alloy 625 because that has been an industry standard in terms of surface protection in these types of units. However, it's not always applicable in all environments and is also not necessarily the most economical or viable option to install as a surface metallurgy upgrade. That can be when we're thinking about the time it takes to do the application. It can be the temperature resistance, if you see higher surface metal temperatures in the boiler. It can be with abrasion erosion, where the alloy 625 tends to suffer from more accelerated or faster metal loss from abrasion erosion. It can be to do with the fact that you don't want to put any heat stress into the boiler using a welding technique. It can be the weight factor if you don't want to install a 3mm thick layer and rather you'd look at a 0.5 millimeter layer of thermal spray. So there's lots of considerations to take into account. And what you can see in the photograph is an example of a waste to energy boiler where they were burning household waste. This is an area just above the refractory line, and in particular in the membrane in between panels, where you tend to have a wider pitch between the tubes. And so the metal in the center of that membrane is at a higher temperature, and that's because it's further away from the cooling effect of the water wall tubes. And in that zone, you can see the installed 625 weld overlay has rapidly broken down and actually created a hole through the membrane wall. In the zone where we have the thermal spray installed, this has a higher temperature capability and so is resisting that environment. So alloy 625 is naturally a system to think about, but there are alternatives in the marketplace that can outperform alloy 625 and provide a viable alternative to alloy 625 as a solution in these environments. When we think about thermal spray technology, a question often comes up is it really a viable option? Thermal spray technologies have a checkered history in boiler applications, and that's mainly due to the quality of the application standard that's been applied and also the class of technology that's been used. IGS, over the 35-40 years of our installation of thermal spray systems in boilers, have understood the limitations of the different thermal spray technologies and class of technology and the different application techniques throughout that process. So we understand from experience which systems work and which systems don't work. So in this slide you can see 4 micrographs across the top showing systems that IGS have used in the past which were not successful in the types of environments we're talking about with biomass or waste to energy boilers, burning fuels with, for example, high chlorine content. These systems haven't worked because the class of technology was not suitable. Through that process and the development of conveyance systems for high velocity thermal spray, so we get the dense microstructure, and in alloy modifications, so we reduce the internal stress of the applied system, we eliminate the microcracking or the macrocracking, and we reduce the amount of oxides in that thermal spray layer. We're able to create an impermeable barrier that is a barrier to the operating environment and that functions as a high nobility alloy on the surface to protect the underlying water wall tubes from metal wastage, from corrosion, but also from erosion. The example I'd like to show you in this presentation is from a waste to energy plant in Switzerland that was a new build plant in 2015. And what this example demonstrates is how an alloy 625 overlay is not always the right solution to operate in these environments, and how a high velocity thermal spray system has actually extended the life of the shop applied and installed alloy 625 in order to prevent the client having to do panel replacements or tube replacements in the boiler. So from the conceptual design, this boiler was intended to be a very low maintenance unit. They didn't want to have extended shutdowns. They were trying to achieve extremely high uptimes, above 97%. In order to do that, they eliminated or they took out all refractory in the boiler. because it was considered and from the operators that the refractory was often the weak point in the unit when it came to repairs and outages. And it was always the refractory repairs that took the time and extended the shutdowns when they had to have the boiler out of service. So with no refractory, they installed alloy 625 shop applied cladding all the way down to the grate level inside these waste energy boilers. So started operating in 2015, but within 2 years, by 2017, they already started to see some challenges in terms of accelerated degradation of the 625 overlay. So the client undertook a study to have a look at what options were available to them, and in 2017 they decided to do initial applications using thermal spray technology in the different boilers. So they had 2 lines on the plant and they had 4 sidewalls effectively of the boilers. So they installed thermal spray systems on each of those sidewalls in order to assess the performance. After 1 year of operation in 2018, we went back in to do a full inspection, and what was obvious from that inspection was that the thermal spray was performing well and was protecting the alloy 625 underneath and preventing the ongoing degradation of the alloy 625 overlay. So at that point, the client decided to extend the application areas of the high velocity thermal spray into a wide area inside the unit. So from the original application in 2017, we had the inspections in 2018, further application, the same in 2019. And 2020, again, we went back into the boilers in order to do some wider application and to further inspect the original applications that we did. So this is after 3 years of operation inside these boilers. What we were able to see was that there had been no degradation, no breakdown of the installed high velocity thermal spray cladding in the same areas where prior to that the client was measuring a loss of up to 0.5 millimeter in certain locations of the 625 overlay. So that overlay was originally installed in 2015 at 3 millimeters thickness. So they would have lost that protection and potentially lost those tubes within 18 months if they hadn't installed the high velocity thermal spray protection system. So over the 3 years that that's been in service, there was no measurable loss of material. So the weld overlay underneath is still maintained at the same thickness, the tube integrity is still there, the thermal spray is still able to operate. The high velocity thermal spray system is applied at a thickness of 0.5 millimeter. So there's also the benefit to the client of this system not installing so much weight into the unit, and the flexibility to be able to apply the system over larger areas on each outage, as the application speed is approximately 3 times faster than you can achieve with weld overlay. So in the first line of the plant, the thermal spray systems have been installed, and in the second line that's also going to be extended. And the client sees this as the technology that he can utilize in order to facilitate the high uptime of the plant that he requires and to provide the preventative maintenance strategy that he needs to get between his annual outages. The next step is to increase the time between intervention. So to move from a 12 months to an 18 months, and I guess ultimately a 2-year outage schedule in order to increase the availability of the plant and the profitability of the plant. So the purpose of these solutions, the alloy upgrades, is in order to help develop preventative maintenance strategies, to extend the time between outages, between the requirements to go in the boiler and do the inspections, do the NDT checks, to raise the confidence of the water-wall surface protection, to prevent the requirement for panel replacement and the challenges that that can bring in doing that in a standard outage, and also to increase the reliability. The main benefit for the client is the installation of a system that is maintainable, that is flexible in the sense of offering quick repair or extension of the application area, and optimizing the return on investment in installing that surface metallurgy upgrade. As we said at the start, IGS have a very broad history and experience working in boilers, over 40 years. We are situated throughout the world, so wherever you may be and wherever you might be listening to this presentation, we can provide our services and our support in your location. So please don't hesitate to contact us if we can be of any service. So thank you very much for listening to our brief presentation. I hope it gave you a quick overview and understanding of what high velocity thermal spray can potentially do in order to protect your boiler when you have a change in fuel composition or you're changing the fuel characteristics. We'd be delighted now to take any questions that you may have, and we look forward to hearing from you if we can support you in any way. Thank you.
So we now welcome Colin back on stage.
Hello.
Hi, Colin. And we have some questions for you. First question from Simon. Hi, Colin. How would you recommend protecting the rear wall boiler tubes against flame impingement in a PF-fired boiler if changing to a slower burning fuel?
Yeah, it's a good question. It is one of those aspects that, as Gerry referred to, you have to consider if you're changing the fuel composition. Flame impingement is typically an aggressive wastage mechanism and can be damaging, obviously very damaging to the water wall tubes. So we have experience of using the high velocity thermal spray claddings to protect tubes in those areas. In some cases, it's where you get increased erosion because of the flame is carrying with it particulates. In other cases, because you're seeing higher temperatures in those locations, which can then potentially cause damage to the original alloy material, or in some cases to a higher nobility alloy. So a couple of examples I can think of is where the customer started burning some MBM fuels in the boiler, and so they were seeing flame impingement on the opposite wall and an increased level of corrosion, but the combination of erosion corrosion. We've installed a protective cladding on that surface to mitigate that. But it is a challenging situation, and we have to look at the individual conditions to understand if it is applicable. But in the vast majority of cases, I would say yes, we have a solution for that.
Thank you, Colin. And we have a good question in the chat from Dave. Do you have thermal spray adhesion and spalling problems with a 625 alloy application? Advice on prep and experience.
Yeah, obviously when you're applying onto a material like that, you have to take particular care of the surface preparation. You have to understand and look carefully at the original condition of the surface. So if you do have damages in the 625 that need to be, for example, addressed prior to the installation or the application of the thermal spray cladding on top, those need to be done. And that's really just having some experience and understanding of what the surface conditions have to be. In terms of the application, the surface preparation techniques we follow are aggressive, in the sense we do an aggressive blast to generate the profile and the cleanliness that we need. With the application itself, because you're applying onto a high nobility material, you can't use direct measurement techniques, which is what we would typically do if we're going onto a carbon steel. So there you're relying also upon the experience of your technicians in order to apply the correct thicknesses and in the right locations of the material. So when we did the inspections on top of a 625, we also have used PMI techniques to identify, what we're measuring on the surface is in fact the C276 base material rather than the 625 base material. So there's certain things you have to take into account when you're carrying out that application, but we do have a lot of experience of doing that. You saw that example from Energia. We've also done it at a number of other plants and facilities where they have 625 installed. So yes, there are specific things you need to manage carefully in terms of your quality control in order to ensure you don't get the type of problems that you're referring to from an adhesion and a spalling point of view.
Thank you, Colin. Question from Mark, and hello from Yorkshire as well. Is it possible to measure erosion and or loss of overlay? Does EMAT or EMAT work? Thank you.
That's a good question. To be honest, I don't actually know if that type of electromagnetic technique can be used to do that. I mean, typically what we see clients using is obviously your standard direct UT inspection measurement techniques rather than mapping techniques. We have some clients who use scanning technologies like laser scanning technologies, but with those you obviously need to have the boiler in a good condition, or at least the walls in a good condition to get a good data point to start off the scanning processes. And then there's various corrosion monitoring mechanisms that clients use in order to look at or to try and measure the rates of metal loss. I don't personally have experience with EMAT to do that, and perhaps that's something that Gerry or a couple of the other speakers might be able to help with in the round table. But certainly we'll look into it. I'll speak to my colleagues who have a bit more knowledge in boilers, and we'll come back to you with our feedback.
Thank you, Colin. Question from Kim. Do you have any calculation or measurements to predict the life of a tube?
I think everybody has a calculation to do that. Obviously, it's highly dependent upon your operating environment and can be dynamic. It's not often a fixed or a static process, because it can depend on the location in the boiler. It could depend on whether you're seeing slagging and under deposit corrosion, or if it's an area of erosion. What we see, a lot of applications that we do, or in fact all applications we do, we go back to do inspections and we monitor the performance of the layer that we've applied. If it's purely a corrosion environment, then typically that's just ensuring that the barrier is maintained as an impermeable barrier. If it's erosion, then we're measuring the amount of loss that we see to the cladding over time, and then we can make predictions on when we need to refurbish. And in some cases we will apply thicker layers in locations where we're seeing higher rates of metal loss, like for example in the corners, around the soot blowers, etc. But in terms of the tube calculations, you'll find lots of examples of ways to do that, but it's obviously very specific to the environment and your boiler.
Thank you, Colin. Question from Tim. Have you any data on surface temperatures of the materials you are speaking of? I have found that steel temperatures, particularly in superheaters, are much higher than thought.
Yeah, so I mean, typically our experience with our materials, we're working at tube metal temperatures up to 500 degrees C. I think a little bit more we've done on a couple of superheaters. Boilers, typically you're operating lower, around sort of 400, 420, 30. Once you get above that 420, 30 degrees C level, and sometimes with a change in fuel, if you get a higher calorific value, you can see that change in a surface metal temperature. Then you can start to see some of the effects that we've been talking about in that example with the alloy 625. So the temperatures above that level, it starts to lose some of its strength and therefore becomes more susceptible to damage. You start to see some of these faster rates of metal loss. In terms of superheaters, etc., we've done numerous applications and have some feedback on that. So if you have a specific environment you'd like us to look at, we can do. Obviously, when we're talking about pendants and superheaters, there's access issues to doing applications on site. So typically, those are pieces of equipment we can apply the system, in the workshop prefabrication rather than doing it in situ. If it's an uncooled surface in a boiler, if it's like an erosion barrier or plate, then typically those can't be protected because the surface temperatures are too high. And what we've done with a number of clients is they've taken away the barriers and actually just applied the erosion barrier directly onto the water wall or onto the tube. So eliminated the baffle plate or the erosion barrier, I'm trying to think of the right word, I think that's what it's called, and just replaced it with the coating on the tube, and so avoided that problem in that way.
Excellent, great answer, Colin. We'll take one more question, and same as Gerry, if you can then answer some of the questions by typing your answer, and we'll go through all of them during the roundtable at the end. Right, sure. So for now, last question from Hannes. What is the best solution using your thermal spray coating on a blank membrane, or should there already be an alloy 625 layer? And then what is your experience with alloy 310?
I mean, it depends on the design, typically, of the OEM. You know, whether you have a surface protection metallurgy in place, or whether you design the tubes from a different metallurgy. You know, what type of is the base material for the water wall. A lot of boilers will have initial zones designed for obviously refractory protection, and then they'll have a section which is from original design as a 625. Obviously, there's a cost associated with that, so it tends to be minimized as much as possible. And often what we find is you start to see problems above that original overlay protected zone. In terms of different tube materials, yes, we have experience with all different types of tube materials in terms of applying our systems on top in order to protect them.
And I guess it doesn't matter if it's applied on a bare tube or there's already
No,
protection
absolutely.
there.
No, absolutely. I mean, probably we're sort of 50-50, something like that. I mean, we've coated more black carbon than we have 625, but in general boilers, for example. But in waste to energy, because there is a lot of 625 installed, it's more like a 50-50 split between applications we've done onto bare tube or applications onto 625.
Excellent. Thank you very much for your answer.
Okay.
And now we'll welcome Ulf from ECOMB, who will show you how to mitigate new combustion issues introduced with a new fuel, cut fuel costs, and reduce pollutants. And share that now.
Hello. Okay, so you will put the...
I will put your presentation up right now, Ulf.
Yeah, okay. So
thank you. And then we'll see you at the Q&A in about 15 minutes.
Yeah, thanks. Welcome to the Fuel Masterclass webinar. My name is Ulf Hagström, and I'm the Managing Director of ECOMB AB in Sweden, an engineering company. Let me introduce the EcoTube system, the tool for fuel switch. The EcoTube system comprises EcoTube assemblies, which are basically water-cooled lances, EcoTubes, equipped with multiple air nozzles for injection of air or recirculated flue gas with high velocity in the furnace, and it penetrates through one of the walls, most often one of the side walls, and the EcoTubes goes from this side wall to the opposite side wall, so it's penetrating the entire cross section of the furnace. The EcoTubes are water-cooled lances, and they are retracted for cleaning every 2-3 times every 24 hours, depending on the fuel, and one cleaning operation takes about 1 minute, and then the EcoTube is back in operation again. We also have a main control cabinet for controlling the whole process. Most of the cases we have included a SNCR system, so it's basically 2 different technologies combined in one, overfire air system and SNCR in one package. The SNCR agent could be ammonia or urea or ammonium sulfate in aqueous forms, or ammonia in anhydrous form, 100% gas. We have a cooling pump skid where the extracted energy from the cooling system will be transferred to a secondary circuit, which goes to a district heating net to increase the temperature on the feed water, or heating up the primary or secondary air, or whatever is suitable for each individual case. And we have the process air fan, which delivers the air or recirculated flue gas to the EcoTubes and further into the furnace. Here is an EcoTube assembly in real life. It's from the Västervik power plant, and you could see the EcoTube in the outer position, having just gone through a cleaning cycle, and the whole system is protected with glass doors. Let's look at the low heating value for some kind of fuels. With oil, it's around 11 kilowatt hours per kilo. Coal, we are down to 7 kilowatt hours per kilo. Biomass as wood pellets is around 5 kilowatt hours per kilo. And biomass as wood chips, where moisture contents are around 40 to 60%, is only at around 2.5 kilowatt hours per kilo. And 1 kilowatt hour is 3.6 megajoules. If we look at a 100 megawatt boiler, we can see a very big difference in flue gas flows depending on moisture content in the fuel, and also the oxygen level in the flue gas, the stoichiometric ratio. In this bar chart, you can see, if you look down to the left, 10% moisture content, you have a flue gas flow of 47 kilos per second with 4% O2. The blue chart, 54 kilos per second at 6% O2, and so on. So if the moisture content for a coal fuel, which is around 10%, you are down to the left, and you are planning to retrofit the boiler for biomass. If you have wet biomass, it's probably a good number around 6, in some cases maybe up to 8% O2, and then you can see that the flue gas flow is doubled more or less. So that means that you need to utilize your furnace volume more efficiently, or you have to increase the furnace volume. So how can you keep the same power output with the new fuel? If we talk about the conversion from coal to biomass, this could be a typical furnace where the biomass is supplied and burned on a sloping grate. The flue gases and combustion gases are always orientated towards the exit, and finding the easiest way to the exit. So that means that you get recirculation zones, often up in the corner near the roof. You can see in the upper left corner where the flue gases are more or less just standing still in a recirculation zone, and you get another one towards the rear wall. So in those zones, nothing happens, and you don't utilize these volumes. If we introduce an EcoTube system, in this case 2 EcoTubes at 2 different elevations, the lower EcoTube, we have air jets directed down towards the front wall, which forces the combustion gases and flue gases to change direction towards the rear wall. And in the upper EcoTube, we do the reverse, so that the gases are forced towards this upper corner where we didn't have any flue gases in the first place. So thereby the furnace volume is maximum utilized, and the residence times are significantly increased. How can the thermal efficiency be maximized? How low can you actually go with the O2 excess air with the new fuels? The EcoTube will inject much less air than you have with your existing overfire air system. So the oxygen content will significantly be reduced, and the turbulence will be maximized at the same time. So you need less excess air to make the same job. If we go even one step further and introduce oxygenated air, or even pure oxygen in the upper elevation, well, we will make calculations for this bit of extreme case, so we can't say, we haven't done any tests so far, but it's an interesting solution to keep the flue gas flow at a real minimum. Of course, when you talk about a conversion, you need to comply with more stringent emission regulations, certainly for NOx. So how can the NOx be reduced for your new application? If we introduce FGR, flue gas recirculation, through the EcoTubes, or from the rear wall or front wall, it will not be a very big reduction for a large unit, maybe around 5 to 10% reduction of NOx. Air staging, which we just talked about, means some 15 to 20% NOx reduction. If it is combined with SNCR, ammonia or urea injection, we can get another 40 to 50% reduction. So in total we are up to 60 to 80% reduction possible for this conversion. Ammonia as slip, we have seen more and more stringent regulations. Still there are plans up to 20 milligram per normal cubic meter, but we believe very few new requirements will be less than 10, and probably less than 5 milligram will be required in the near future. The ammonia consumption is of course an OPEX. It's a quite significant cost over the years, so how much can that be reduced? We have seen up to 50% less costs for ammonia, for instance. CO and LOI, loss of ignition, is of course important when you talk about thermal efficiency improvement, and there we can make a real good effort, up to 80% less. CO2, if we split it into combustion related, it's not a big change. It's reduced fuel flow basically, and when the oxygen content in the flue gas is reduced, then you get you need to put in less fuel for the same output. CCS is a new technology that will come for sure, and here you can get up to 100% reduction when you take care of all the flue gases. So that means that it will be very important to keep the flue gas flow as low as possible. What about the EcoTube economics? We have talked about increased thermal efficiency and reduced O2, which is obviously a reduced cost, OPEX. Increased output. How can your output be maximized with a low calorific fuel compared to what you have today if you have got coal? It's of course important. Radically improved emissions and associated fees, such as NOx fees, which we have in Sweden and in some other countries too. CO2 trading systems will probably increase also in US now, I guess. Reduced costs for adding CCS technologies we have mentioned, and it's about minimizing the flue gas flow as much as possible. Another interesting thing is that we can reduce the cost for fly ash disposal, which means less fly ash in the flue gas. You can't get rid of the inorganics, but you can change it from fly ash to bottom ash or slag. Thank you very much for listening to this, and don't hesitate to get back to us with questions. So thank you very much.
Thank you, Ulf. Excellent presentation. So we have some questions for you. First question is from Pavel. What is the maximum safe operating temperature in the furnace for EcoTubes?
There is none, basically. We can, if you are up to 1500 degrees C, it's all about the cooling system. So it's we can say that there is no, in practice, upper limit of the gas temperatures inside the boiler.
Thank you, Ulf. Question from Mark. Is EcoTube installation applicable to a PC boiler?
Oh yeah, of course. It's all system that has got an overfire air system. We can we will be able to optimize the burnout in the overfire air level all the way up to the superheater level. And even so, if the temperatures are too high at the inlet of the superheaters, we can install the EcoTubes inside the superheater bank. We have done a lot of calculations, but no installation so far. But we are confident we can inject ammonia or urea at the right temperature, and that's critical for the SNCR process. So we are flexible there.
Thank you, Ulf. And it's also applicable for CFB boilers?
CFB boilers we have not done before, but the erosion effects, we thought that would be a showstopper, but small tests we have carried out with with simple tubes, I guess it will not be a significant issue with the erosion, but we haven't installed anything in a CFB boiler yet, so we don't have a reference there, but I mean, we don't believe that.
Thank you, Ulf. A question from Kim. If the EcoTube is installed, is it not dangerous if there is positive pressure in the furnace?
Yeah, we have a tightening in the wall, so it should be a real high pressure if going through that tightening. So that was one of the early issues we had to solve, but it's solved since several years now.
Excellent, thank you. And question from Tim. How did the EcoTube system affect the standard deviation on the steam generation?
I don't think it's... we have while the EcoTube are water cooled, we transfer this energy, which is approximately 50 to 100 or 50 to 200 kilowatt per meter of EcoTube. That's a ballpark number, and where you put this energy as increasing the temperature of the secondary air or tertiary air or the feed water system, you always gain, or you always put the energy back in the system again. So that always, we have done many different solutions for that. So it's not a big issue.
Thank you. Question from Munawar. How can EcoTube reduce LOI? I believe that's loss on ignition?
Yeah. That's, well, if you have a more efficient combustion process, you have a radically improved turbulence. You, of course, will convert the carbon on the fly ash particles more efficiently and reduce the LOI. So if you have a more efficient burnout, you will reduce CO and LOI for sure.
Thank you. Question from Andreas. Do you need to perform any major studies like CFD studies before designing EcoTube for a specific plant modification?
Yeah, that was one of the question I expected to get, because the process is like we get in touch with the plant, we ask for information, for drawings, for Excel sheets, what about CO, NOx at different O2 levels, different boiler loads, everything. But then it's in most cases not enough. You need to study the process in detail, and therefore we have developed a special video camera, which is a very useful tool to visualize the process in different operation modes. So that will give us the key information. In some cases, certainly for a new boiler where we have installed one of our latest installation at Martinique in the West Indies, it was a completely new boiler. Then, of course, we have to rely on CFDs, which we do, so we can decide what elevation we would install the EcoTubes and how many and so on. So it's an engineering work before you can make that final decision.
Thank you, Ulf. We'll take one more question from Suresh, and if we have any more questions, Ulf will either answer them in the chat and or during the roundtable at the end. So hi, Ulf. What is the frequency of using this EcoTube system?
The frequency, I'm not sure what he's meaning by frequency. If it means it will stay in the boiler 99.9% of the time. So if one EcoTube is retracted for a cleaning operation, which takes about 1 minute, and then it's back again. And for coal, for biomass, it's about maybe one operation per 24 hours. But for waste, which is more challenging fuel, you probably need, or our experience say you need 3 or 4 cleaning operations every 24 hours, but it's still just 1 minute. So you have to make a small compensation for that minute when it's out of operation.
Mm-hmm. And just a follow-up question from Suresh, will the system work on a tower boiler design?
Tower boiler design, I can't see. We have installed EcoTubes from front wall, from side walls, so I can't say we have studied the tower design more deeply, but we will be happy to look further into those possibilities.
Excellent. Thank you, Ulf. And we look forward to welcoming you back at the Q&A. So our final presentation will be delivered by Vince. So just a quick introduction slide. So Vince Barreto is representing power plant cleaning systems, and he will explain how the buildup of slugging on convection surfaces in boilers and heat exchangers can be eliminated. Hi, Vince.
Hi, thank you.
And your presentation is about to start.
Hello, my name is Vince Barreto, and I am president and owner of PowerPlus Cleaning Systems. I'm going to talk today about pulse detonation cleaning and how it provides a safe and effective alternative to other boiler cleaning methods. Typical challenges in boiler operation result from the burning of solid hydrocarbon fuels that result in the slagging and fouling of downstream heat transfer surfaces with excessive ash deposits. If left unchecked, the mass fouling will cause to redirected flow patterns and loss of efficiency. Excessive cleaning via the traditional soot blowing methods can cause thinning or pitting of the tube surfaces, eventually leading to tube leaks and expensive and unplanned outages. Pulse detonation or impulse cleaning has proven to be a different and a much more effective approach than other existing cleaning systems being used. This section will provide a brief background and description of the impulse cleaning technology, an explanation and placement of operation, and highlight the significant benefits and advantages gained by the implementation of the impulse cleaning systems. The pulse detonation cleaning system is a derivative of the pulse detonation propulsion development at GE's Global Research Center. I served as a global product manager at GE Energy back in the early 2000s and observed that the typical acoustic cleaning systems did not have sufficient power or scope to clean large coal-fired or waste-to-energy boilers with its tenacious type of deposits. In 2004, we began an initiative to adapt the pulse detonation technology to a more powerful cleaning system. We were able to commercialize that system in 2006, and since then there have been well over 150 installations made on boilers. Pulse detonation cleaning provides several advantages. It is non-erosive to the surface, so you can be very proactive in the cleaning. Typical cleaning cycles are every 30 minutes to an hour. The shock waves are extremely encompassing and penetrate deep into the tube bundle, as opposed to traditional soot blowers that have more of a line of sight cleaning. It's orders of magnitude much more powerful than a traditional acoustic cleaning system, And there are no moving parts, so there's no costly repair, maintenance, or operational cost. It doesn't scavenge steam that is meant to use for creating energy, and its ability to run in a very proactive manner or back off and run in a very regimented manner and still be effective at dislodging deposits deep into the tube bundle has provided a very great advantage. As I just mentioned, the typical challenges with soot blowing are the effects of platinization between the tubes where the soot blowers don't have direct access. Also, aggressive soot blowing or soot blowing in general over time can cause tube erosion and pitting that will eventually lead to thinning of the tubes and tube leaks. Our approach to pulse detonation cleaning is very simple. It is essentially an engine that was adapted from the GE propulsion side. We are mixing gas and air in a combustion tube and igniting it, and we're not storing the pressure, we're not pre-compressing the gases. Everything is done as it passes by the ignition, and this allows us to run a series of rapid impulses very effectively. It is that piling of impulses, and usually between 20 to 30 impulses, that creates these a massive amount of cleaning energy and competing pressure vectors that are very effective at dislodging the ash. There are a few approaches to pulse detonation cleaning. Our approach is to take and inject the gas and the air and mix it at the mixing head. There is no pressurization of the gases, and this allows us to create a series of rapid impulses, one after the other, very quickly. This is also advantageous in the cleaning effectiveness of those impulses. The alternate design would pre-compress gases in separate tanks and then combine them and ignite them under high pressure. This provides the need for multiple gases, moving parts that eventually have to be maintained, and there is a restriction of flow as that has to make its way down the center tube to enter the boiler, and a loss of the overall pressure entering the boiler. Cleaning with a shock wave consists of compression and rarefaction waves that are omnidirectional in their scope. So when a single shock wave is produced, you have a highly compressed front followed by a rarefaction or low pressure following that, and then a trailing eddy current or vortex that creates sweeping action following that high pressure front and the low pressure swing. So that change or displacement and the eddy current behind it create a large amount of opposing vectors or pressure swings that will serve to very effectively dislodge deposits. That was one shock wave. We do this between 20 or 30 times in a single cleaning cycle, providing an excessive amount of cleaning energy. A typical system consists of a control system that monitors the impulses and puts the system into a fault within 1.5 or 2 seconds if it notices that there is something that is not operating correctly. It doesn't matter if it's a lack of gas or a bad igniter. It doesn't allow uncombusted gas to be injected into the boiler. It also tracks the pressure in the flow in the supply line leading up to the unit, so if there is any small leak, it will also put it into a fault. There are many safety factors that are built into the control system to prevent any problem from happening. Typically, there's a 1/2-inch supply line for gas and a 1-inch supply line for compressed air. We do use plant air. We do not require instrument air. And then a gas rack or fuel manifold is required at ground level, and multiple bottles would be manifolded into a single supply line. Typical consumption of gas is obviously based on the operation that is programmed, but most generally anything that is ran at 20 impulses every 30 minutes would go through a 30-pound bottle of ethylene about once every 10 or 12 days. And each cleaning cycle, a 30-second cleaning cycle, would consume about 40 cubic feet of compressed air. The cleaning system consists of a combustion tube where there is a mixing head that brings the gas into the side and the air with it comes in the back and mixes it, and then there's an igniter directly in front of that ignites it as the gas mixture passes by. It is connected to bell sections that have a diverging flare to them so that you can shape and direct the impulses into the boiler. The typical application of the impulse cleaner would be to insert it into the lane between the two bundles, much like the subblowers would be. The shock wave then would exit the face of the cleaning device and expand in every direction. We're able then to get deep into the tube bundles, unlike a subblower, with the shock waves being more encompassing. Typical placement on the side of the boiler is about every 4.5 to 6 meters apart. We're able to clean approximately 7.5 meters wide by about 10.5 meters in depth. Of course, that distance can be mitigated based on the distance between the tube bundles, so each installation will be a little bit different based on the configuration and the reflected energy that occurs. This is an example of an impulse cleaner installed on the side of a waste to energy boiler. Here it's installed in an access door. It can be installed in a subblower opening or a inspection port opening. Generally, we're looking for areas that provide access to the open space between the tube bundles. And I'm going to show the video here of the unit in operation. This is a 20 impulse cycle. Depending upon the installation, the external noise levels will rise to somewhere around 90-95 dB. If this were on an air heater or an area of a hopper where there is much less insulation, that sound level can increase within 3 meters of the back of the device on the outside to as much as 103 to 106 dB. Here's an example of an impulse cleaner installed through a soot blower port on a large CFB boiler. And here's a video of the unit actually cleaning with the doors open. We were on that same exact CFB boiler. We were doing an install in November, and the doors were open as we were doing the installation, and we were cycling the impulse cleaner as we were dialing in the gas and air pressure. So we only ran about 6 or 7 impulses, not the customary 20 impulses. And looking across the lane, you can see the opposing access door and the light shining through from the other side. Once we start to cycle, just a few cycles, and it should be noted that this facility actually paid a contractor to come in prior to us installing our units and clean with detonation cords. So this was a clean boiler that we were commissioning our systems on. And this video will show an example of the amount of material on a clean boiler we were able to dislodge. Well, I've greatly appreciated the opportunity to show this technology to you and look forward to discussing any questions or final thoughts that you might have as we open it up for questions.
Thank you, Vince, for the presentation, and would like to welcome you on stage.
Thank you.
Thank you. To answer some questions, I see you've already started. So we'll go to the ones that are unanswered right now. Question from Mar. Would the plant structure require to be modified to avoid any effect from the shock waves?
No, the shock wave itself is the cleaning energy, but the pressure that is generated from the shock wave is absorbed in our combustion tube. The high cycling is the tube is engineered for that high cycling. Again, it's essentially an engine. The shock wave that enters the boiler and the pressure that enters the boiler dissipates at a very quickly as it enters a large cross section. So the amount of pressure that's actually introduced to the boiler exerted on the tubes or the structure is minimal. It's the shock wave with the highly compressed gas front, the pressure leading the shock wave, and then because we've highly pressurized the leading the gas in front of it, then there's a low pressure behind it, and that's that swing or displacement that, as in the sweeping energy of the negative that it follows, that causes it to be cleaning, effective at cleaning. But this all happens in the gas column or air column as it passes through the boiler. It has a negligible effect on the actual hard surfaces that tend to reflect or it encompasses around the shock wave that wraps around and encompasses the tube structure. So there's and of course the biggest thing I could say is that we have 14 plus years now of actual installations where we can show that that it has no effect on refractory and or tube or the vessel structure itself. It doesn't require any additional stiffening or an engineering study to determine if it's going to cause damage.
Thank you, Vince. Question from Kanagaraj. What is the difference between sonic soot blower versus impulse detonation cleaning?
It's a very large difference. I have quite a bit of experience with the acoustic cleaning because that was one of the items, one of the product lines I was a product manager for since the early 90s, and very familiar with that technology. If you were to compare the shock wave or the pressures created when we create the detonation for the shock wave and the pressure created by the minimal displacement or swing in pressure that occurs with a sound wave, if you calculate the pressures, it's somewhere on a 75 hertz acoustic cleaner. That swing in air pressure is extremely minimal, maybe 1/10 of 1 psi swing. In comparison, the pressures exiting the front of a pulse detonation cleaner are around at least our approach to pulse detonation cleaning are about 40 psi, 40 to 45 psi at the face. Again, that 40 to 45 psi within a meter of the front of the device drops rapidly to maybe less than 1 psi because we've entered a much larger cross section and that pressure is widely dispersed. But it's not the pressure doing the cleaning in this case. We're not relying on that. We are relying on this displacement or high swing in pressure. So the initial shock wave now is moving at Mach 5 throughout the boiler and reflecting off of the other around the tubes, encompassing those tubes. And we're cycling at such a rate, 20 or 30 impulses, 2 per second. It's programmable. We can run more per second, or we can run more impulses. But that piling of shock waves, one behind the other, is what has proved to be very effective at dislodging the particulate.
Thank you, Vince. Impulse cleaner shock waves being more encompassing, do they alter the air profile within the boiler?
They do not change your air profile. Again, the amount of the cross-sectional space in the boiler and the pressures that we're introducing are negligible to the large cross-section. So it imparts. It's not even, the instrumentation won't even see that. It's not going to change your pressures that you're monitoring within your boiler. Typically what you will see though is a large displacement or removal of particles of ash and a higher flow capacity throughout the boiler without restriction.
Thank you, Vince. Great answer. Question from Michael. Do you have installation experience for waste to energy boilers, especially high temperature parts, including the superheaters?
Yes, we do. We have multiple installations on waste to energy, both RDF and mass burn, biomass, wood, and other applications such as that. There is an advantage with waste to energy with our proactive cleaning approach. We have found that the ability to clean every 30 minutes, as opposed to maybe sublow every hour, 2 hours, 3 hours, where you allow the material to build up on itself and create a structure, it is much more difficult with the tenacious type of deposits you get with waste to energy to try to dislodge them after they've set up in place. So the proactive approach, keeping the material entrained in the gas stream and moving through the boiler, has proven to be very beneficial at maintaining cleanliness instead of trying to dislodge a lot of material after it's had a chance to center and build a structure. So we've proven to be very effective in waste energy.
Thank you. Next question from Mark. Have you used your system on air heater baskets, hot end and cold end?
We have not yet applied on air heater baskets for Lundstrom style or basket style. We have some tubular installations to maintain cleanliness of the tubular air heater, but the Lundstrom or basket style air heaters, not as of yet, although I have experience with those applications from my time at GE. I understand them, and I'm highly confident that we would also provide a similar improved result in those applications, and we would be willing to work with customers to design a system to prove that case.
Thank you, Vince. Question from Colin. Does the system have to use ethylene, I believe? The formula is C2H4 from the bottle, or can other fuel gases be used? The storage of this gas might be problematic.
Yes, so the answer is yes, it does need ethylene. For the system was engineered based on ethylenes. If we were to use other fuels, propane or natural gas, they have a slower flame speed, and in order to get to detonation and the small cross-section, the small profile we have, and the short distance in our design, it requires a gas with a higher flame speed, such as ethylene. Other gases could work in our profile, such as acetylene and or hydrogen, but those are not gases for safety reasons, we choose not to use those other two gases. There are advantages to the ethylene as far as cost, and its forgiveness, unlike propane, has a wide range for combustibility, so it makes it extremely reliable that we're maintaining the detonation throughout the cycles with the ethylene. As far as the challenges with the storing that compressed gas, it is adding a flammable gas to the jobs, to the work site, to the plant, that has to be evaluated. But just like any other gas that are used for welding or other flammable gases on site, those are steps that aren't overly problematic, and many of the plants have been able to work through those easily. Again, the system has several safety features based on to ensure that there's not uncombusted gas being put into the boiler, but also tracking and monitoring flow rates. So if there is a very small leak, the system is set up to sense that and then close the main header valve immediately until that leak is addressed and repaired. It will not run if there's a small leak in any of the supply line from the supply rack up to our unit.
Thank you, Vince. A question from Mark. Would the impulse cleaning reduce the use of soot blowing 100%?
In some cases it has. I mean, many companies will first try it, they stick their toe in the water, I guess you would say, by installing our systems and evaluating how effective they are as compared to the soot blowers. And ultimately, many do pull the soot blowers out. So I would say that it's very likely we can replace the soot blowers. I think the challenges that we might have would be in the same areas that the soot blowers are having challenges on, frankly, in the hotter sections above the bullnose, where you're, in the case of coal, above the deformation temperature of the ash, and you get slag and molten slag deposit. We're not going to be very effective at dislodging slag unless you're using a modifier for your fuel, like mag oxide or something like that, to provide some friability. Then our systems could work there. But as far as, you know, augmenting the soot blowers, absolutely. Reducing or limiting, extremely limiting the use of the soot blowers, but in many cases, totally replacing them is possible.
Great answer, thank you. Question from Simon: is pulse cleaning effective on close pitch fin tubed economizers?
Yes, it is very effective. Again, because it's so encompassing, the shock wave is less, you know, without a soot blower has more of a line of sight cleaning, which provides great difficulty with fin tubes because of all the surface area and the angularity of those surfaces, where the shock wave is much more encompassing. So we actually have a great advantage with fin tubes over traditional types of cleaning. In fact, a large part of our business is we've adapted this technology, the pulse detonation cleaning system, and put it on a hood, a directional hood, and a large part of our business is involved in going into combined cycle plants with HRSGs that have fin tube arrangements and cleaning those 18 to 22 tube deep, fin, very tightly compacted arrangements that are typical in a HRSG, cleaning those offline very effectively with the pulse detonation cleaner. So we have a lot of experience and success at cleaning fin tubes.
Thank you, Vince. We'll take one more question and then we'll welcome Gerry on stage to summarize the event before our roundtable.
Well, we hope you found this of interest. And if we just summarize the key sort of points from today, it's all about setting up a protocol to ensure that you don't miss anything. And the key building blocks to this are understanding the fuel. If you can understand the fuel, you'll then be able to identify the high risks to your plant, and from there you can look at mitigation. You need to be aware that as the fuel switch becomes more complicated, maybe you're moving towards a 20 or a 50% replacement or even 100% replacement, you will have to do more work, and there will be costs associated with that. So the very simple fuel switch is a desktop study. The 100% conversion, you're looking at a feed study. But the key point is, if you identify and manage the risks, you can do fuel switching. Fuel switching is relatively easy. I just remind you that there are people in the market who can help you if you aren't that familiar with different fuels. So this is where the workshop ends, or the presentations end, and I'm now going to pass you over to our colleague Marina, who would sort of manage the Q&A session that we're going to have now. Thank you for your participation.